Good day, everyone. We'll be looking at theory of structures 3, and this course will cover statically determinate structures and indeterminate structures. When we say statically determinate structures, that is, we'll be determining the reaction of beams and their shear force and bending moment as well. While for the indeterminate structure, we'll be looking at the analysis method of complex beam or structures, and we'll be using different analytical tools like the moment distribution method and the slope deflection method. There are other tools that we can use, some of which include matrix method, maybe using stiffness method or the flexibility method, but the scope of this course will not cover that aspect. So let's go straight to the point. I've explained determinate structures and indeterminate structures that we'll be covering. Now, looking at a simply supported beam or statically determinate beam, I believe we can all recall how to determine the determinacy of a beam using this formula, 3m plus r. When it is less than 3j plus c, that means the structure is statically unstable. But when it is equals to 3j plus c, as we have in this second state, that means it is statically determinate. And when it is greater than this, it is indeterminate, where r is the number of support reaction, the c is the equation condition, while the m is the number of members and j is the number of joints. And I think you can see, or we can also use this one, r equals to 3n. I think we can still remember this one, where n is our the total number of parts we are considering, and r is the total number of forces under consideration. An example is this, having this particular beam. For this one, this is a single member, as you can see. That is why our n equals to 1. And the number of reactions, this is a pin support, and this is a roller support. So for a pin support, we have how many unknown? I said we have 2. And for a roller support, we have 1 unknown reaction. So when you have this one, using this formula, r equals to 3n, since our r equals to 3 and n equals to 1, 3 times 1, we have 3 equals to 3 times 1. So definitely it's under this condition, so it is statically determinate. So the same thing applicable for others. You can practice this one. For this particular one, it's still a single member, but we have the fixed end here. So for a fixed end, we have 3 unknown, and for a roller support, we have a single unknown. So when we have 2 roller support, that is single here, making 2, plus the 3 unknown reactions at the fixed end, making 5 altogether. So our r equals to 5, our number of reactions is 5, and in how many members we have is just a single member, so our n equals to 1. So for this particular one, we have r to be greater than 3 times n. So what does that say? It says it is statically indeterminate, as we can see here. When your r is greater than 3n, it is statically indeterminate. And now this brings to mind, so what degree? So how do we know the degree? All we just need to do is just remove the r we have here and minus 3n. What do we have? 5 minus 3, that's 2. So it is indeterminate to the second degree. We have done that before. This is just a refreshment, or to refresh our memory on what we have done before. So you can look at this, and then you can do the calculation. 3 3 2 2, like that. You can do the calculation and come up with your result. So let me go straight to the business of the day. We want to look at we have an idealized structure here. This let's look at this structure here. Now this deck or this slab is supported in one direction, and look at the way it is. You can see this A, B, C, D, E, F. These 3 beams, they are supporting this slab, and the slab is having a load of 5 kilonewton per meter square. And if you look at it, all these three beams, they are being supported under this beam EF and beam BF here. So all of this girder BF. So, and each of these girder is resting on this column that we have here. Now, how is the load? How is it being distributed? For this slab we have here, let's look taking this surface with related to this beam 1, 2, and 3. Now, if you want to put it in an idealized form, we have it A, B, C, D, and EF. Now, this AB, which is the beam, this outer beam, is what load is it going to carry? As I demonstrated the other day, that if three people are carrying a beam or a plank, and somebody is at the edge, another person is at the center, another person is at the other edge, that the person at the center will be carrying half of the weight to both front and back, while the person at the front will just be carrying half from here to here. So the same thing applicable to this slab. This beam will carry just load from here to here, this shaded portion here, like this, while the what's it called, the CD, it will carry this particular load here. So now, how do we calculate the load? It's very simple. All we just need to do is, what is the span? The span from here to here is 3. So from here to here is 3. So if from here to here is 1.5, from here to here is 1.5. So what will this one carry? This one will just carry this to 0.75, and we were told that it's 5 kilonewton times 5 kilonewton per meter square. That is, for every meter the load is 5 kilonewton. For every meter square is 5 kilonewton. So how do we now look at how is it being distributed? How do we draw the free body diagram? Now let us start with this particular beam CD. Look at the beam CD we have here. This CD, so is carrying 0.75 plus 0.75, that's 1.5. So how do we know the UDL that it will carry? So all we just need to do is multiply this 5 by 1.5. So once we do that, it will give us 7.5. That's the UDL that will be carried on this particular beam CD. Now, and this CD, it spans 3 meters. So what load will be carried on this support C, and likewise on this support D? So it's very simple. Since it's 7.5 kilonewton per meter, to convert it to a point load, it will be 7.5 times 3. That will be I think 22.5 or so. So which will be the total load on this particular beam, a total point load of 22.5. Now, since it's simply supported, each portion will carry half of that 22.5, and this one will carry half of 22.5, which will leave us with 11.25 on this side, 11.25 on this other side. Please mind you, we are considering this beam CD. Now let us now look at this girder. This girder we have here, we have BF and AF girder. Now let us consider this girder, AE and BF girder. Now let us consider this girder AE, that is this one here. This is the girder we're talking about. Now, to consider this girder, what load is it going to carry? Mind you, this one is at this CD, we were told that it's carrying 11.25 load at the center here. So what load will AB carry at the center here? The same way we did this calculation, 5 times 1.5 for this, we will do for this particular AB, which should be 0.75 times 5 kilonewton per meter square. That will give us 3.75 or so, or thereabouts. Now we will now multiply that okay, 5 times 0.75 will give us 3.75. Now that 3.75 will be what we have here. Now what load will be carried at the support A, and what load will be carried at support B? You know, the same condition that happens to AB is what is applicable in point EF. So for this particular one, we multiply that 3.75 by 3 meters. 3.75 times 3, which will give us 11.25. That is, the total load will now be 11.25 if we are considering beam AB. So if we have 11.25 total load, what load will now be carried here will now be 11.25 divided by 2, which is equal to 5.625. So we have 5.625 here, 5.625 here, and we have 11.25 here, which is what we have here. So that's what will be happening at this gather AE. So you can see we have 5.625, and 11.25. So that's the way this beam will be loaded. So I hope that is clear enough. Look at it and just digest that before I proceed to the next point. So all those explanations for a one-way slab system. So we have another wonderful scenario, that is, let us look at a two-way slab system. So a two-way system. Now looking at this one, this is an example of a two-way system. In this particular scenario, we have it is carrying 5 kilonewton per meter square, and it spans 3 meter. Now how is the load being distributed in a two-way slab? Unlike the other one that we have a single beam, but for this particular one, they are all carrying the same load. Let me say the load is distributed in this format because it's a two-way, that is, they distribute the load equally. So let's say we have 4 people carrying this particular slab. Each one will carry this particular point of load. However, it is possible for us to have a situation whereby it is not square. You know, this one is square, 3 by 3 meters. It's possible for us to have a situation that is not square, maybe a rectangular scenario. Maybe this one is 3 meters and it spans 5 meter breadth. How is it being distributed? We draw this angle 45 degree, and then we meet this angle 45 degree of the short span where they meet. Then we draw a straight line, and likewise do the same thing for the other edge. So we have something like a trapezium. We'll still see that example, but for this particular scenario, let us look at the calculation just like the way we did the other time. We have 5 kilonewton per meter square, and if I multiply it by 5 kilonewton times 1.5, what will I have? 5 kilonewton times 1.5, we have that's, I think, 7.5 or so. So we have 7.5, and it will be loaded in this triangular form here. 7.5 will be at the top here. So we distribute it based on this loading. So for this particular one, it's very simple. To know the load, we can always say half base times height. Then we divide, and that will be the total load. Then we divide it by 2 to know what load is carried at each point. So when we get to that side, I will explain that one better. Let us go ahead. I said to show how to treat this case, we consider a square reinforced slab as shown here, which is supported in 4 by 4 3 meter long edge beam, and here L2 over L1, that is the long span over the short span, is 1. That is because it's square. 3 divided by 3 is 1. So, and then we have it, as you can see, the 45 degrees that is mentioned of the other time. So we have a uniform load of 5 kilonewton per meter square, and then 5 kilonewton times 1.5 will give us 1.5, which I've explained. Now the other case that I was talking about is this rectangular case, when we have 4.5 meters by 3 meters. You can see the angle 45 degree and the angle 45 degree here. Now when we have that angle 45 degree where they meet, then we then draw a straight line like that. So how is this one going to be treated? It's very simple, the same way we did that. We just look at 5 kilonewton times 1.5, we have 7.5. That's the UDL at this center here. Then we distribute this way. But for this particular point BD or AC, we have it this form. So you can see the way it is, and we can do a calculation for each support to know what we have there. So I believe that is very clear enough. You can try that, and then you can let me know what you have there, what you have in your support at point A and point C, etc., etc. Any question? Okay, let's go to the next one.